Good morning. Today's video lecture is going to be about the derivative as a function. So this is going to be a little different than the video from last time where we were finding the value of a derivative at a point. What I mean there is we were finding, if we just had a graph and we had a function, I was finding the slope of a tangent at, say, a specific value like x equals 2. What we're going to do today is we're going to figure out a way to find a function that will give us the value of the derivative anywhere. So this will be the derivative function that we're going to learn how to find. The process is actually very similar to what we just did. It's just a little bit more general. So let me erase this. We'll get right in. So here we go. We'll start off with a picture. In fact, I'm just going to draw the same picture. In fact, I could probably teach 80% of calculus with this picture right here. So now, instead of saying, I want to know what the slope of the tangent line here is at this point x equals 2, I'm just going to say it's x equals x. Any old x value. And what we're going to do, just like before, we say, okay, if I'm interested in the slope of that tangent there, I'm going to pick another point that's a little bit away from x, and I'm going to say it's x plus h units away from x, or it's h units away from x. And it's a secant line, which I'm going to make green. I don't know if you guys can see the distinction between the colors there, but this one's blue, or this one's green and that one's blue. And then this is the exact same process before. We want this green secant line to become that tangent line, so what do we need to do? We need to make the distance between these 2 points approach 0, but not equal 0. And the way we do that is with the limiting process. And so here's our formal definition of f prime of x. And if you notice, it looks very similar to what we did before. It was the, I think, equation 3.6 that the book named, equation 3.6. But the one in equation 3.6, this was a specific value of x here. Like maybe it was x equals 2, or maybe it was x equals 1, or x equals pi. A specific value of x. But when you do this limit on a function, your answer is going to be a function that we call f prime of x. It's also known as the derivative of y with respect to x. Like this right here means the derivative with respect to x of y. We typically just write it like that, dy over dx. It's the slope of the tangent at any x. Okay? It's the slope of the tangent at any x. So we're going to erase the board here, and we're going to work out a couple of examples to show you how to compute f prime of x using this technique. Those of you that are in physics, you may have learned some shortcut rules. I haven't talked to Mr. McManus yet about if he's taught you these shortcut rules. There are shortcut rules for computing these derivatives, and we will learn them, trust me, and you will love them. But we're going to go through doing a few this way, the old long way, first. So we'll pause, and we'll be right back. Oh, hey, caught me drinking some coffee here. So we're back. Here's our example that we're going to do. It's a parabola. F of x is 2x squared plus 3x minus 1. And we're going to find f prime of x. So that's what the directions would be. Find f prime of x. And we're going to find f prime of x using the limit definition. Okay? So let's get after it. Here we go. We're going to say the limit as h goes to 0 of, and I'm going to move out of the way so you guys can see this a little better, f of x plus h minus f of x over h. Okay, so what do we have to do here? We got to use this function and compute this limit now. So f of x plus h, well, by this point, you know that f of x plus h means take x plus h and f it. And I say that in like it sounds inappropriate, but it's actually quite mathematically sound if I say f x plus h, because it's applying the rule of f. That's what we say as mathematicians. F just stands for function. Okay, here we go. So, oh wait, let's back up. I just have f of x plus h right here. I need to subtract off up here in this expression right here. I need to subtract off f of x, which is 2x squared plus 3x minus 1. Okay? And I like to put this f of x in parentheses when I do this limit here. By the way, this is called a difference quotient, in case you're wondering. You'll hear me use that term every now and then. Okay? This is called a difference quotient. But I like to put this in, when I'm computing the limit of a difference quotient like this, I like to put this f part in parentheses. So now this is just, you got to put your algebra pants on here and get after this. So I'm going to expand that. I'll distribute the 3. And then I'm going to distribute that negative. And then don't forget about that all over h. So I'll give you a second to digest that and make sure you got it all. There's a lot there. But this definitely requires some big algebra pants. So now I'm going to distribute that to 2x squared plus 4xh plus 2h squared plus 3x plus 3h minus 1 minus 2x squared minus 3x plus 1 all over h. Okay, now, if you did this right, magic is going to happen, because all of these terms up in the numerator here, all of the terms that don't have h in it are going to disappear. So watch this. 2x squared, negative 2x squared. 3x, negative 3x. Negative 1, plus 1. Okay, so check that out. Now, this limit simplifies. I'm going to go up here. This limit simplifies to the limit as h goes to 0 of 4xh. Whoops, you can't see that. 4xh plus 2h squared plus 3h, and that's it, all over h. And now, we still can't just plug in 0 for h because we're going to get 0 over 0. But if you see real carefully, if you look real carefully, you'll see that, hey, there's an h in the numerator that I can factor out and remove that. And so now those h's cancel, and you're left with this. Okay, so all of this mess, this horrendous looking mess right here, ends up just becoming this right here, that limit. And I can make h go to 0 on that real simply, because nothing bad happens. If h approaches 0, that would approach 0 right there, and what are you left with? 4x plus 3. Okay? And friends, this is equal to f prime of x. The derivative function for this function right here that we started with, his derivative function is 4x plus 3. Now, let's talk about what that means, because we never do all this work, and we're like, oh, yeah, I got the answer, and then don't know what the answer means. What does this answer mean? This answer means, like, say if I found f prime of 1. F prime of 1. 4 times 1 plus 3. That's 7. F prime of 1 is 7. What does that mean? That means if I were to want the slope of the tangent to this function at x equals 1, it would be 7. Okay? Maybe I wanted to write the equation of that tangent line at x equals 1 to this function right here, to the original function f. So in order to write the equation of a line, I need a point and a slope. So I've got a slope here. What's my point? My point would be f of 1. So I go back up here to f, and I look at what would f of 1 be? 2 plus 3 is 5, minus 1. 5 minus 1 is 4. So my point is 1, 4. So my equation of that tangent line would be y equals 4 plus 7 times x minus 1. Okay? So that's the equation of that tangent line. This method here, once I get this equation, it eliminates me having to do that limit definition of derivative at a point that we learned the other day. And again, eventually we're going to learn shortcuts to go from here to here. I knew the answer to this before we even started this. And you will too, probably this time next week. So I'm going to pause the video here. I'm going to erase the board, and we're going to do another example involving a radical. And then, yeah, so I'll be right back. Hello, we're back. Got another example here, and a different color. Used blue this time. I've noticed that when I was writing, I don't know if you guys picked up on this, these markers, they write a little thinner, so I can use less space when I write. But they squeak. I don't know if you can hear that on the board, if the microphone's picking that up, but I'm sure from home it sounds really, really weird. Of course, your Chromebook sound probably stinks and you can't hear anything. So, so here we go. Here's our function. We're going to find f prime of x. Okay, and we're going to find it using that limit definition. Again, we're going to learn shortcuts for this. Don't worry. I always, when I'm computing a derivative using the limit definition, I always write it down because it'll help you memorize it. It's a good exercise to write down every single time. The limit as h goes to 0 of f of x plus h minus f of x over h. The limit of a difference quotient. So here we go. So we got to take x plus h and f it. So that's f of x plus h, right? I mean, that's not too horrible looking. And then here's f. Okay? And now we're here. And folks, we had one like this on the homework a couple days ago. In fact, I believe maybe one or two of you even contacted me and asked me about this. How do I deal with this? I can't just plug in 0 for h. I'm going to get 0 over 0. How do I simplify this, or what do I do to this so that I can compute this limit algebraically? And we're going to pull out an old trick from algebra, multiplying by a clever form of 1, what we call the conjugate form of 1. Okay, so I'm taking this expression here and I'm multiplying it by 1. Okay, this is 1. I mean, yeah, it looks horrible, it looks horrendous, but it's a really ugly one, but it is 1. Whoa, no it's not, because this should be x plus 1 here. Now it's 1. This is 1, right? And it's the conjugate form. What do we mean by the conjugate form? Well, if you notice, I have something here something minus something else. And then right here I have that same something plus something else. It's like a minus b, a plus b. It's a difference of two squares factored. So when I multiply those together, I'm going to get a squared minus b squared. And that's what we're going to do here, and it's going to simplify really nice. Okay? So again, you're going to have to pull up your algebra pants here. So I've got this radical times this radical. Well, it's the same radical, right? So it's just x plus h plus 1. And then minus this radical times this radical. Again, same radical, so it's just x plus 1. And over h, and then times that hot mess. Okay, and just leave it factored. Don't try to simplify this. Just leave this as x plus h plus 1 plus radical x plus 1. Just leave that factored in the denominator. Just leave it like messy. It's okay, because it's all going to clean up real nice. Here we go. Now look at the numerator. X minus x. 1 minus 1. So the numerator, you're just left with h. And then what's the denominator left with? H times radical x plus h plus 1 plus radical x plus 1. I don't know if you guys can hear that. The markers are kind of annoying. So there we are. Check it out. And just like before, my friends, just like before, if you do this right, the h's are going to cancel. You're going to be able to factor out an h in the numerator, and the h from the original definition is going to cancel out. If you do it right, you'll know you did it, because that'll always be there. You'll have an h over h that you can cancel out. And then what are we left with here? What are we left with? I'm going to go across here. Also, you'll be able to see it better. So I'm going to go across. I'm going to say this is the limit as h goes to 0 of 1 over the square root of x plus h plus 1 plus the square root of x plus 1. Now, look at that. Look at this expression here. Okay? Can you do this can you now compute this just by substituting in 0 for h? And some of you may be struggling right now with answering that question in general. How do I know when can I just plug in 0 for h? Well, you can if nothing bad happens, like you get 0 over 0, or like you get a 0 in the denominator. And a 0 in the denominator wouldn't even necessarily be bad, because it could end up being infinity. But if you get 0 over 0, you can't plug in 0 for h. But now, look right here. Look. If I plug in 0 for h here, I'm just going to have x plus 1 there, and then x plus 1 there. So what am I going to be left with? 1 over the square root of x plus 1 plus the square root of x plus 1. And I feel like we could just simplify that to 1 over 2 square root of x plus 1. There we go. Yeah. Perfect. Okay, so what is this answer? This, my friends, is equal to f prime of x. So if I started with this function up here as radical x plus 1, the derivative function for radical x plus 1 is 1 over 2 radical x plus 1. And again, there's a shortcut. You don't have to go through all this. We're going to only do this for a couple days. A day or two, and that's it. We'll learn some shortcuts, and we'll be able to compute these derivatives lickety-split, okay? So what we've done today is I've shown you 2 examples on how to find the derivative function using the limit definition. The next thing that we're going to learn, the next video after this, is we're going to start to look at, and we're going to spend some time on this, we're going to start to look at how is the graph of this derivative function and the graph of that original function, how are those related? how are those graphs connected? It turns out that the derivative tells you a whole lot about the function, and maybe a little, and somewhat vice versa a little bit too. So we're going to connect these graphs. In the next video also, we're going to talk about that. So what would that be? Well, that's going to be the derivative of the derivative. And it turns out he's connected to the original function. How these things are all intertwined, that's what we're going to learn about next time. So for your problems for this section, which I believe is 3.2 in your textbook, we're going to spend a few days in 3.2. All I want you to do for 3.2 is 54 to 58, 60, 62, and 63. Okay? And then we'll probably talk after you guys watch this video during class today, because I think you're going to watch this during class today. So I'll see you soon. That's it.